So in this video we are going to see what is Bertrand's postulate. And before that we are going to see the gaps between primes, the definition, the results, the research progress, and then finally we will try to prove Bertrand's postulate. So in this part we will be doing the statement and the initial part of the proof. Okay, so what is a gap between primes? You know, the primes are the sequences 2, 5, 2, 3, 5, 7. It goes like the property that it is not divisible by any other primes or any other numbers. So primes are divisible by them and 1, right? Yeah. So we are now talking about the gaps. That means if you have a prime, then how much we want to travel to get another prime, right? So that's what we call a prime gap. Okay, so a gap between primes p and q can be easily say it is the difference p minus q. So it can be any prime and q be any other prime. So we say that what is the difference? P minus q, right? So right, so without loss of generality we assume q is less than p. So p minus q would be the prime gap between any two primes. I'm now telling the consecutive, right? So here we see some examples. 3 minus 2 equal to 1, 5 minus 3 is 2, 11 minus 7 is 4, right? Yeah. So the only even prime is 2, right? Otherwise, if you take primes p and q greater than 2, then these gaps is always even, right? Because p primes are odd numbers except the number 2. So the difference of odd numbers going to be an even number, right? It will be an even number. Okay. If it involves 2, then it would be odd. Otherwise, if you take two prime numbers greater than 2, it will be, the difference is always even. Okay. Next, what is twin primes? So the pair of primes PQ are called twin primes if the difference is 2, right? If p minus q is equal to 2, I'm using the modulus, not mentioning which prime is greater. Okay, so if the modulus of p minus q is 2, then we call that this is twin primes. These are some examples. This is twin prime pairs 3, 5, 7, 5 and 11, 13, right? Now we don't know whether there are infinitely such primes, right? So we know that there are infinitely many primes. You know, the Euclid's proof and many other proofs are given, and but we don't know whether these pairs are infinite. Okay, so that is what we called twin prime conjecture. Twin prime conjecture. That means, are there infinitely many primes? That's a question. Okay. How do you prove it? You have to show that there are infinitely many by some idea. If there are not infinitely many primes, then you have to find a bound. a natural number. So, and more than that, there is no twin. So these are the ways to prove, but nobody has proved yet. So twin prime conjecture is a still standing conjecture. Now the question is, are the gaps bounded? For example, I mean, since primes are infinite, an arbitrary gap never bounded, because that's the meaning, right? Arbitrary gap may not be bounded, but I'm asking whether the consecutive gaps. So here I am addressing not an arbitrary gap like 5 and 2, 11 and 3, not like that. I'm asking like this: 7 minus 5 is 2. Like these kind of gaps, consecutive gaps. Consecutive. Are they bounded? For example, suppose I say that the nth prime, n plus 1 prime minus pn is less than 70. That means you take any consecutive pair, the difference is always 70. So there may be infinitely many primes, I don't care, but if you take the consecutive difference, less than 70. So that's what the question, whether is there such a number available? That's the question. So right, so we can see that these gaps cannot be bounded, right? So this is the question I want to ask. Is there exists a constant m such that for any two primes p and q it is bounded? It is not actually any two primes, any consecutive primes. Consecutive, because that's very important. Any two primes, definitely it is easy to see that it is because there are infinitely many primes. You can make this gap always arbitrary, because you take a prime number p, and since primes are infinite, for you fix an n, and of course I will get a prime number q from. So then the gap is at least n. So that's not a question. If you have an arbitrary gap, I mean, you take a prime from here, you take a prime from some other, then that gaps are always unbounded. But the question is consecutive gaps. Consecutive gaps are bounded or not, right? So it is a negative answer. Prime gaps are not bounded. I mean, these consecutive gaps are not bounded. So here we have a result. Maybe we can easily prove that for each n greater than or equal to 2, there exists a kth prime, right? So I mean, what I'm trying to say, that you will always get a prime pair p, I mean, you will always get a prime pair pk, consecutive primes. You always get a consecutive prime such that their gap is at least n minus 1. That means at least n, whatever, depends on what, right? So for a given any natural number, you will get a consecutive prime having this distance apart. So how do you prove that one? So proof is it's a constructive proof. It's very easy. We are going to observe something like this. Observe that these numbers are consecutive and a composite. That's the idea. So n factorial plus 2, right? And n factorial plus 3, and n factorial plus n, right? So n factorial plus 2, you can see this is 1 times 2 times up to n plus 2. So this cannot be a prime number because 2 divides it, right? 2 is a factor in both the sum, so the total sum is divisible by 2. Similarly, in this case 3 is a common factor. Finally you get n is a common factor. So definitely these numbers are consecutive, right? N factorial plus 1 plus x factorial plus 2 plus 3, they are consecutive and they are not prime numbers. So you got how many of them? We're starting from 2, right? So there are n minus 1 consecutive composite numbers. So this you can construct, depends on n, right? Any natural number n, you can construct these numbers, right? So now how do you get the pair, the prime pair? That's very easy. You choose a prime less than this n factorial plus 2, right? This is some kth prime, I don't know what is a k, right? Maybe it's second prime, third prime, I don't know. It depends on n you will get. So this k is depends on n, right? Whatever the n you choose, it depends on n. Okay, and you choose a prime which is greater than n factorial plus n. So that would be your k plus 1. And why it is a k plus 1? Because not the least number. You choose pkn or pk which is less than n factorial plus 2, but it should be the maximum, the maximum prime number. Okay, so the greatest prime number less than n factorial plus 2, that is pk. Okay, greatest prime number less than n factorial plus 2. Similarly, this is the least prime number greater than n factorial plus n. What is pk plus 1? pk plus 1 is the least in that set. So this pair has the distance at least n minus 1, right? It should be definitely n minus 1 because n factorial plus 2 is not a prime number, of course. N factorial plus n is not a prime number. So the distance should be at least n minus 1. So this n minus 1 depends on any, we can find always pk plus 1 and pk, right? This is a pictorial representation I am giving. So what we have found that the prime gap, the consecutive gap is not bounded. I mean, for any n you will get prime pairs which is at least this distance apart. Okay, so that's not bounded. Okay, yeah. Now recently Yitang Zhang, a very mathematician, proved that he proved some result. So that's very a breakthrough in prime, the research in number theory. So that was like this. So the result is like this: the limit infimum of n tends to infinity, pn plus 1 minus pn, right? It is less than 7 times 10 raised to 7, so 70 million, right? Yeah. So what is the meaning of this one? I am not going to the whole concept of limit inferior or something, but it is something related to the consecutive primes, right? That you understood. Okay, so yeah, so what is the meaning of that? So meaning is very simple. Yitang Zhang proved that there are infinitely many pairs of primes that their gap, right? So they are consecutive prime numbers, so that their gap is less than this number. For example, I don't know, for say there are infinitely many pairs pn plus 1 and pn and pn plus 1, such that their gap is equal to 5. Suppose I am telling, I don't know that the theorem just telling that there exists some number there exists a number where this property is satisfied. Okay, That's what they're telling, right? So okay, yeah. So there is such pairs exist. So I'll just give you a glimpse about limit inferior. This is very simple. You suppose you take Gn to be Pn plus 1 minus Pn, right? Then limit infimum means you are creating a set, for example B1. So this is Gn, Pn plus 1 minus Pn, that's our sequence, the prime gaps, consecutive gap, the gap between consecutive primes. So B1 is starting from G1, I mean P2 minus P1, P3 minus P2, like that is going. And B2 is, you are avoiding the first gap, then G2 starting from P2 minus P3 minus P, like that. So that is the sequence, that is the set we have built. Now we are trying to find out the infimum of this. So infimum of this set means that is a minimum, okay, not minimum. If somebody is not familiar with the infimum, we can talk about the minimum number, okay. So these are definitely subsets of natural number. Then by well ordering principle it has a minimum number, right? That's very important, okay. So right, so it has a minimum number, it is bounded below, so that it has a minimum number, and B2 has a minimum number. So definitely infimum of B1 would be less than other one. So if you assume, if you say Cn is infimum of Bn, then C1 would be less than or equal to C2, less than or equal to Cn, like, because the first infimum is taken all over the set, all over the numbers G1, G2, and next you are avoiding the first fellow, then you are finding the infimum, right? So definitely the first one is more smaller. So this is an increasing sequence, and what Yitang Zhang proved that this sequence converges, right? So he proved that this converges to a particular number. That number is not, we don't know that number, right? So that's what it is. So suppose we say that it is going like C1, C2, then at a particular time it will be CK. So then that CK is less than 70 million. So what is the meaning? If that CK is some number 7, that means there are infinitely many pairs that prime pairs having that, right? So having the gap 7. So that's the meaning of that theorem, right? Okay, so that's the proof, and I have just to rewrite that thing, Zhang's theorem, telling that there are infinitely many pairs P1, P2 of distinct primes, such that P1 minus P2 is less than or equal to 70 million, right? So definitely if you say a consecutive difference, then there are infinitely many, so there is no problem telling there are infinitely many pairs P1, P2, distinct primes. The gap, they are less than or equal to 70 million, right? So that is talking about the minimality, okay. I mean yeah, okay. So finally, after proving such a groundbreaking result by Yitang Zhang, then they proved that there are infinitely many pairs P1, P2 of distinct primes, such that the distance is less than 246. That's very amazing, right? So the collaboration between mathematicians across the world able to reduce the 70 million into a very 3-digit number, 246. So the power of collaboration was amazing. So that program was called Langland's program. You can check all this in internet. So these are the results between gaps. So why I am interested in these gaps because the Bertrand's postulate is maybe the first result which is talking about gaps, because Bertrand's postulate telling that whenever you start with a number, suppose you start with a prime, and the next prime cannot be more than the p distance, right? So when I start search p, start searching from p, then p plus 1, p plus 2, p plus 3, then before I reach 2p, I definitely get a prime p, a prime q. That's what the Bertrand postulate is telling. So not for a prime, not for any number, for any natural number, there is a number, there is a prime number between n and 2n. So you start from n, then the next prime, right, you will you don't have to count more than 2n. In between there is a prime. So this equality is only for because n is 1, because here n greater than 1, right? If n strictly greater than 1, this inequality, this can be avoided. Okay, it's because we admit n greater than or equal to 1, we can say n less than, p less than or equal to 2n. Okay, so there is a prime between n and 2n, right? So this is the statement of Bertrand postulate. So we are not starting the proof because, right? So with the next lecture onwards we will start the proof, and we will complete in at most four parts. Okay, so this is the idea. So for example, I will give you start with 2, then you don't have to you go for 4, so definitely you find a prime number. This is the most obvious case because 2 and 4 in between 3. We start from some 5, definitely you don't have to reach 10, there are many primes, 7, so you start from 15, so you don't have to go 30 because definitely you will get 19 as a prime. So that's the proof, right? That's the theorem. There is something, but you have to prove this formally. How do you prove it? There is always a prime between n and 2n. Okay. Okay, thank you.